All right, welcome back to part 2. Let's talk about logarithms. The definition of a logarithmic function with base a says that for x greater than 0, a greater than 0, and a not equal to 1, y equals log base a of x if and only if x equals a to the y. All right, so our definition says that x equals a to the y is the same as y equals log base a of x. We're going to keep this in mind. We're going to use it repeatedly. The function given by f of x equals log base a of x is called the logarithmic function with base a. Now, if we look at this, right, y equals log base a of x. All y is an exponent. So all a logarithm is an exponent. All right, that's it. A logarithm is just a fancy way of writing an exponent. So let's go back and forth writing logarithms in exponential form. Log base 7 of 343 equals 3. The log is base 7, so our exponential is base 7. The log equals the exponent, so 3 is what is equal to the log, so 3 is our exponent. This is bad notation over here. Log equals 3, but it's the basic idea. What's the logarithm equal to? Well, that's what our exponent is. So 7 to the third equals 343. Also, we could say 3 is the power you raise 7 to in order to get 343. All right, so base of the log, base of the exponential. The log is the exponent, so the 3 is the exponent, and then the 343 comes to the other side. Log base 16 of 8 equals 3/4. The base is 16, so the base of our exponential is 16. 3/4 is equal to the logarithm, so 3/4 is our exponent. And we raise 16 to the 3/4 power in order to get, so equals 8, the 8 that remains. The thing about logs and exponentials is here we have, on the exponential part, we have the 8 by itself, whereas inside the logarithm, it's not. So we go back and forth between logs and exponents, exponential functions, in order to rearrange and isolate different parts of it. Whenever the base of the log is unwritten, it's assumed to be 10, because we have 10 fingers and most of us have 10 fingers and 10 toes. It's just a common base to use. So log of 1 over 1,000 equals -3. As there's no base written, it's assumed to be a 10 base. Log equals the exponent, so -3 is the exponent. 10 to the power of -3 is equal to 1 over 1,000. All right? Always say the words as you're writing it down to see that connection. Log base 8 of 4 equals 2/3. Base is 8. Log is 2/3, so the exponent is 2/3 to get 4. So 8 to the 2/3 power equals 4. And if you're putting this in your calculator, 8 and then the caret, that little up arrow above the division key usually, make sure you put 2/3 in parentheses if your calculator doesn't show it already in the exponent. So put parentheses around 2/3 and you'll get the 4 and you'll see that it's correct. Let's go in the opposite order. Write in logarithmic form. So 13 squared equals 169. The base of the log is the same as the base of the exponential. So 13 squared tells us it's log base 13. 2, the exponent. 2 is what the logarithm is equal to. So 2 in green is the power. All the logarithm is a power to which I raise 13 in order to get 169. Next one. 9 to the 3/2 equals 27. We'll write this as 3/2 is the power, so logarithm, to which I raise 9. 9 is our base of the exponential. 9 is the base of the logarithm in order to get 27. 3/2 is the power. All a log is a power. To which I raise 9. So it's our base. It's written a little bit lower. It's like the basement. It's a little bit lower than everything else in the house to get 27. 4 to the -3 equals 1 over 64. Our base is 4. Our exponent is -3. To get 1 over 64, this would be -3 equals log base 4 of 1 over 64. And I have no idea why I didn't circle that in red like the other ones, but whatever. Give that one a try. If you are pretty confident in your answer, go with it. And if you're not very confident, send me a message and I'll let you know that you're right. All right, some properties of logs. These are called basic fundamental properties of logarithms. First property, log base a of 1 equals 0. Because if we think about this when we rewrite it, the base is a, 0 is the exponent. Anything that is not 0 raised to the 0 power is equal to 1. So log base a of 1 equals 0 because a to the 0 equals 1. Moving across, number 2. Remember, a log is just a power. So this is saying the power to which I raise a in order to get a must be 1. And our verification over here in exponential form, a to the first equals a. Now, number 3 is partially due to the definition. What power, right, log, what power do I put on a to get a to the x? Well, the power is x, right? So that's what it equals. Log base a of a to the x equals x. Also, log base a of x is the power to which I raise a in order to get x. If you go back to that definition about 6 minutes ago, 5.5 minutes ago, and if you're scrolling, this is exactly the definition, only we don't use the y variable at all. We just use log base a of x in its place. Number 4 is the one-to-one property of logarithms. This is used quite a bit. If log base a of x is equal to log base a of y, so log base a on both sides, same base, then it has to be the x equals y. And we have 4 examples here that will use these properties. Let's get them all on the same screen. What power do we put on 3.2 in order to get 1? Well, that power must be 0 by property 1. Anything other than 0 raised to the 0 power is 1. So if I want to get 1 out of it, then it has to be the 0 power. Log is equal to 0. The base of 9 and log base of 9, they're inverses of each other, so they undo the work. It's like adding 3 and then subtracting 3. So 9 to the log base 9 of 15, using property 3, will give us 15. All right, we call this the inverse property. Number 3, log base pi of pi. So what power do I put on pi to get pi? Well, by property 2, it has to be pi to the first power. Ignore this, what is that called? That's called a jellyfish. Yeah, ignore this jellyfish looking pi. I don't know what happened there. We're going to call that a glitch in the matrix. Log base 11 of 11 to the 7th. What power, right, log, do I put on 11 if I want to get 11 to the 7th? Well, that's the 7th power. It says it right here, the 7th power. Scrolling down through the notes some more. Sorry about the giant spacing there. It wasn't worth the nightmare it was going to take to rearrange that. Here's a fact. The graph of the logarithmic function is the inverse of the graph of the exponential function. For those of you that took Math 120 here at DACC, this was on your final exam. This is something you know. Hopefully it's something you remember, but it's definitely something you know. So if we have an exponential function, f of x equals a to the x with a y-intercept of 0, 1, that means the x-intercept on our logarithmic function will be 1, 0, right? All an inverse does is switch the x and y. The domain of an exponential function is all real numbers, and the range is positive numbers, which means the inverse, right, just switches x and y. For a logarithmic function, our domain will be positive, no matter which version we have, and the range will be all real numbers. So we'll use all the y's, but only the positive x values, right? Domain, positive x values. Other than that base of 10, we have another special logarithmic function. It's called the natural log function, and it uses e, the number that I mentioned at the end of part 1 of this lecture. The function defined by f of x equals log base e of x is written as ln of x. In Latin, it's Logarithmicae Naturalis. L for logarithm. It is not an I, it's an L. It's a lowercase l. But please don't write I. Please, please, please. And the domain is x is greater than 0, and it's called the natural logarithmic function, and the natural log is one of the keys on your calculator, whichever type of calculator you're using. The other log button on your calculator is log base 10. Right? Those are the only two that will show up on calculators. though not every calculator has both. All the properties that we saw with logarithms before still hold with a base of e. All right, one last thing. Let's talk a little bit more about logarithmic functions and their domains. We talked about rational functions and how the domain has denominator can't be 0. And we talked about radical functions, where the radicand, that thing under the radical, cannot be negative. Now we get to logarithmic functions, the only other exception in the domain world. We're going to let a be an expression in the variable x. So maybe it's x squared plus 3x, maybe it's just x, maybe it's 2x minus 1. It's just some expression using x. For the logarithmic functions, given by f of x equals log base b of x, or in particular, f of x equals natural log of a. Sorry, that's an a, that's not an x. I can't read my own typing. The domain consists of all real numbers x, such that the expression on the inside is greater than 0. In this a, it's called the argument of the log. Okay, so the argument, the denominator, the radicand. Those are the places that we look for domains. So the argument has to be positive, not 0, not negative, just positive values. So to find the domain of each logarithm, here we have f of x equals log base 3 of x minus 4. The argument, the x minus 4, must be greater than 0. So we solve the inequality, x minus 4 is greater than 0. Add 4 to both sides to get x is greater than 4. And then we put it in interval notation to get 4 to infinity. Notice they're both parentheses because there's no equal to anywhere. Number 2. For g of x equals natural log of 3 minus 2x. Again, we set the argument 3 minus 2x greater than 0. Let's add 2x to both sides to get 3 is greater than 2x. And then divide by 2 to get 3 halves is greater than x, which looks weird to me. So I'm going to rewrite it with the x on the left side. But notice the inequality is pointing at the x and the 3 halves is greater than x. So I make sure that the inequality is still pointing at x when I switch the order. If x is less than 3 halves, interval notation becomes a little bit easier. 3 halves greater than x is weird, but x is less than 3 halves makes sense in transferring to interval notation. Notice that some of these x values are going to be negative. So the x values themselves don't have to be positive, but when you put the entire expression inside of the logarithm, that expression has to be positive. All right, so not the x itself, the entire expression inside the natural log. All right, let's do another one. This one's going to take a little bit of work and some knowledge of our quadratics, which I know you have. h of x equals log of x squared minus 4x minus 5. Now, there's no base written. So with no base written, it's automatically base 10. That's the first thing you should think is, oh, it's base 10 because nothing's written. But that has nothing to do with domain. It doesn't matter what the base is. We always just look at the argument. So in this argument, we have a quadratic equation. Here we go. X squared minus 4x minus 5 has to be greater than 0. Well, we can factor this as x minus 5 times x plus 1 has to be greater than 0. And we know that x equals 5 and x equals negative 1 will make the expression on the left equal to 0, but we don't want it equal. We want it only greater. Where is this positive? Remember that it's a quadratic equation, right? And it has a graph that's a parabola. Since the coefficient of the squared term is a positive 1, we know the parabola opens upward. So we know that as x goes to negative infinity, the graph goes up, and as x goes to positive infinity, the graph goes up. Combine the known shape of the graph and the location of the zeros at negative 1 and 5 to find that the argument of the logarithm, this quadratic, is positive on the outsides. So negative infinity to negative 1, and then again from 5 to infinity. And you can take a look at the graph to verify that and make sure that you could graph the logarithm, or you could just graph the parabola and see that this is true. That's it for logarithms and my first lecture of this type. So I'm going to post on the discussion board. If you have any questions about any part of this lecture, just let me know which problem, which lecture, which part of it, and we'll go from there.